Hey folks, Ms. Gosling here with an example problem on thermal physics. In this question, I am going to place a 5 kilogram cube of ice. Let's go ahead and highlight important things. A 5 kilogram cube of ice at negative 20 degrees Celsius on a 3 kilowatt burner. How long will it take to heat the ice to its boiling point, which is 100 degrees Celsius? The latent heat of fusion for water is 334 kilojoules per kilogram, and the specific heat of water is 4.19 kilojoules per kilogram. And I'm going to go ahead and in red, finally, highlight the last thing I need. So before I do any of the usual beginning steps for this problem, I'm actually going to go ahead and start by drawing the phase change diagram for this ice cube. So here's my ice cube. We've got heat going into it over, and this change in temperature, so we've got Q and temperature as our X and Y axis. And we're going to start out with our solid ice at negative 20 degrees Celsius. And it's going to get slowly heated until, and its temperature is increasing as more heat's put into it. But once it reaches 0 degrees Celsius, we know that that is the melting point for ice. And so that ice is going to stay at the same temperature until it all turns to water. And then we're going to heat it up again, and it'll end up at 100 degrees Celsius. So we kind of have three portions of our equation here. We've got part one here, which is going to be heating the ice up to its freezing point, to its melting point. We have part two, which is when the ice is melted. And we have part three, when the ice is finally heated up to that final temperature that we want, 100 degrees Celsius. So with that in mind, I'm going to go ahead and start listing out givens. And I'm going to go ahead and do that for part one, part two, and part three. So in part one, we know that the mass of the ice is 5 kilograms. We know that the initial temperature is negative 20 degrees Celsius. The final temperature is 0 degrees Celsius, again, just for part one. And of these two things here, we care about the specific heat of water because we are heating water up, we are not melting it yet. So we are going to say C is equal to 4.19 kilojoules per kilogram Kelvin. So that's for part one. Then we can go ahead and add in part two. So in section two, our mass is the same. It's still 5 kilograms of ice that's getting melted into 5 kilograms of water. We also know that the latent heat of fusion for water here, or LF, is 334 kilojoules per kilogram. And then finally, in part three, we know, again, the mass is 5 kilograms. T initial now is 0 degrees Celsius, since we're still at our freezing melting point. And our final temperature is 100 degrees Celsius, the boiling point of water. And then finally, we're going to be using the specific heat again. So we know C is 4.19 kilojoules per kilogram Kelvin. So these are all my givens. I know it's a lot. And you maybe notice there's one thing we haven't talked about yet. This number here. So if you look at our question, we want to find out how long it will take to heat the ice to reach its boiling point. And so that means we need to end our answer with a time. This information that we have here from our givens is just going to give us the amount of heat required to heat up the ice. In order to convert that to a time, we need this power here. Because remember, our burner has a power of 3 kilowatts, which means that it's supplying 3 kilojoules of heat per second. So we're going to do this at the very end. First, I'm going to go ahead and figure out what Q is. And then using what I found for Q, I'm going to put that back in here and figure out how much time it'll take to put that into our water. So let's go ahead and instead of using my unknown as my time, I'm going to go ahead and start by trying to find again. I'm going to go ahead and try to find Q and then use that to find time. So to do that, I'm going to go ahead and write out my equation. I know that Q total is going to equal I'm going to switch my colors here, guys. Sorry, this is a little confusing. I'm going to go ahead and say that my total heat is equal to MC delta T for section 1 plus plus ML for section 2 plus MC delta T for section 3. And now I can put in numbers. Q is equal to 5 times 4.19 times 0 minus negative 20. And note here, guys, and what's important here, guys, is to remember to include all of your negative signs here, right? So these are going to become positive, and this will be a positive number. It's important, though, to remember that your signs matter. Okay, so let's go ahead and add in our mass and latent heat of fusion. So we have 5 times 334 plus our last MC delta T, 5 times 4.119 times 100 minus 0. And this is just plugging in all of my givens into my equation. And when I do that, I will find that my final heat, the heat required to raise my ice from negative 20 degrees Celsius to 100 degrees Celsius, is 4,184 kilojoules. Make sure you remember our unit here, guys. It's kilojoules, right? Because our latent heat of fusion is in kilojoules, and our specific heat is in kilojoules. And remember, I'm not quite done yet, because my final unknown is time. And that, thankfully, is a pretty simple thing to find. So we know that the power is 3 kilojoules, or kilowatts, which again is 3 kilojoules per second. So if we want to convert from kilojoules to seconds, we just need to go ahead and divide by power. So time is equal to Q over P. And so what we'll find is time is equal to 4,184 kilojoules divided by 3 kilojoules per second, or approximately 1,400 seconds. So that is how long it will take to heat up my ice to its boiling point. Hopefully this all made sense. It is now your turn to go ahead and try solving problems on your own. Good luck!